Hi, this is Ajay Barboza, and this presentation is with regards to a parallel implementation of text clustering using k-means. This is a project that I have undertaken for my pattern recognition course. Let us get on with the slides. So, what is clustering? Clustering models, usually identify relationships in a data set that you might not logically derive through casual observations. For example, you see the figure here. You can logically discern that people who commute to their jobs by bicycle do not typically live a long distance from where they work. The algorithm, however, can find other characteristics about bicycle commuters that are not as obvious. In the following diagram, you see cluster A represents data about people who tend to drive to work, while cluster B represents data about people who tend to ride bicycles to work. Clustering, in a broad way, could be defined as a process of grouping the objects that are similar to each other within the group, but which are dissimilar to any other object in a different group. For example, in the diagram shown below on the right, consider a set of scattered documents. There are three types of documents shown with three different colors, and when you perform clustering on this with eventual requirement of three groups, you see formation of three clusters, each cluster having similar documents. Okay. Now, what is text clustering? Text data is found everywhere. It is ubiquitous. As the volume of text data increases, management and analysis of the text data becomes unprecedentedly important. Text mining is an emerging technology for handling the increasing text data. So it is one of the fundamental functions in the text mining, which is a huge field. Text clustering is used to divide a collection of text documents into different category groups so that documents in the same category group describe the same topics, such as classic music or Chinese history. So, what are the key challenges that we face in this text clustering process? First, the number of available words are large, as a document can be drawn from a lexicon containing 10 raised to power 5 number of words, but the document itself may contain only a few hundred words. This problem is very serious. When the documents to be clustered are very small, you know, we would require to take into consideration that there would be a very sparse distribution of the number of words that we're going to choose from. Now, though the lexicon of a given document is very large, as I said, the words are usually correlated and the number of concepts represented by them are far less compared to the feature set. This poses a requirement of considering the correlation of the words while designing an algorithm. The number of words in a document can have wide variance. Hence, it is important to normalize the document representation appropriately during the clustering. Another challenge is the high dimensionality and the sparse representation of all documents in a corpus requires specialized algorithm for text clustering. A lot of study has been performed and is an active area in the domain of information retrieval. For an effective clustering, it is important to normalize the word frequency by finding the ratio of the number of occurrence in the document to the number of documents it appears in. One way to represent the text document in a numerical representation is to use vector space model. Well, it has its own advantages. Those are, it is easy to calculate the similarity between documents when you use vector space model to represent each document. While its disadvantages are, the terms are each word in a document are assumed to be independent, which is not true in reality. Okay, how do we create this vector space? We see in the top left corner a pool of document which has a large number of documents collection. We process all these documents initially to create a set of unique words. This is shown on the right corner, a pool of unique words from the document collection on the left. Now you pick up each document from the document collection. The size of the vector space is equal to the number of unique words that you have found in the entire document collection. Each document is picked from the document collection, and then every word in the document picked is processed to find a TF-IDF, which stands for term frequency and inverse document frequency. This is calculated for each word in the document, and it's slotted in the appropriate place in the vector space for that particular document. So what is term frequency, inverse document frequency? It is a numerical way to represent how important a word is to a document in a corpus or a document collection. It is widely used in web and text mining as a weighting factor. Term frequency defines the number of times a term occurs in a document. The term frequency can be calculated as a ratio of a number of times a word occurs in a document to the total number of words in a document. Well, the inverse document frequency is number which indicates if the word is common or rare across the documents in the corpus. It is obtained by finding the ratio of total number of documents by the number of documents containing that term, and then taking logarithm of the quotient. So this was the initial phase of processing the document, representing the document in the numerical form, so we could run some clustering algorithm on it. So let us get on with the k-mean clustering, which is used to group these documents. What is the basic idea behind this actually? You choose the value of a k. K means indicates there are k groups, and means indicate that you choose k centroids which represent the mean for each of the group. So you start with you define a value for k, and then you choose k objects randomly from a pool of documents or an object. Then you start calculating the distance of each of the object with the respective list of centroids, and the one with the minimum distance, you place that particular document in that particular centroid list. So while you're done with processing all these documents, you have finally a four, if k is 4, then you have 4 lists, each containing group of documents which are closest to that particular centroid. You keep repeating this. What happens is, once the clustering is done, you recalculate the mean of the centroid by averaging over the entire vector space of all the documents in that particular group, and then you rerun the clustering again. You keep doing this for a finite number of time, or there is a stopping criteria defined, which we are going to discuss in the later slides. So the flow of k-means algorithm. This flowchart gives a good picture of how a general k-mean algorithm works. You read objects from a file, and then you pick the first k objects, or randomly in the case of the implementation that I've taken up, the initial cluster centers. Then for each data object you find the nearest cluster, and then you assign the membership, which basically indicates that you're dropping this into the bucket of that particular centroid which is closest to this document. Then you average the centroid of the new clusters using the objects inside the clusters. You determine, there is a threshold value. This threshold would be defined in the coming slides, or the maximum number of iterations. And this keeps looping, and once you're done, you output the clustering results. Okay. What are the platforms that I have considered for evaluating the text clustering algorithm? I have used two platforms. These are two interesting. One is the Core i7 from Intel, which is the high performance CPU present in most of the desktops today, which has beefy computing power and the cores, while the other one is it's a Telera Tile GX36, which is a 36 core many core CPU, and it is interconnected with a mesh which provides high performance communication between these tiles. So it uses VLIW architecture, that is very long instruction word, and each core runs at 1 gigahertz. They have specialized MAC unit to perform 4 floating point operations per cycle. It is a 64-bit system, with the ability to address up to 1 terabyte of DDR3 memory. This enables the Tile GX to perform number crunching operations in parallel with low power consumption. The peak power consumption of all the cores running is up to 55 to 60 watts. So it is a good platform, highly parallel, to explore text clustering algorithms. So one caveat to this project is implementing this algorithm in a serial version and a parallel version. OpenMP is used for implementing the parallel version. OpenMP is a programming model for shared memory architecture, which is user-friendly, and just by using few compiler directives #pragmas into your existing serial code, you could parallelize the application. Yeah, of course, you need to take care of synchronization and joining wherever the parallel region ends. We will discuss about it in forthcoming slides. So the entire algorithm in nutshell: vector space creation. To begin with, I am using synthetic data here. I have a pool of words and I carve out documents using that. So the first step is to generate the data and then parse each document to create a list of unique words, as discussed before. And once you're done with it, you create a vector space equivalent to the number of unique words, and you perform TF-IDF for each of the word in the document to calculate its vector space. Now towards the k-mean clustering side, which is the next step, you choose the number k, that's number of clusters you want. You process each document to find the similarity with the cluster center, and here I use cosine similarity. There are other implementations which could be explored. After forming the clusters, you recalculate the mean of the cluster center by averaging over the vector space over all the documents that belong to that particular cluster. And then you check, is the new vector, the vector space of the centroid, same as the past